Okay, so we continue with the problem with problems on variable mass. So let us look at problem 2 here. So the problem says the freely moving water droplet constantly evaporates, assuming that the net momentum carried away by the vapor vanishes and that the rate of evaporation is proportional to surface area. Calculate the velocity of the drop as a function of time. Now in this particular problem, so far we have dealt with a situation where a raindrop is accumulating moisture from its surrounding, that is to say when it is passing through a cloud. So it is accumulating the moisture, but in this particular case the moisture is going away from the raindrop. Okay. So the situation is the following: we have a water droplet in which the water evaporates in all direction. Each of this water molecule that leaves this sphere surface essentially carries some part of momentum with it, but because the dispersion is even from all direction, the net momentum cancels out. So the evaporation process does not exert any force on this particular droplet. So we have at time t, we have a mass m, or let us say a mass m, and let us say it has a velocity v, and assuming that there is a radius r, at time t plus delta t, what happens is it becomes m minus delta m. Let us say the velocity has changed from v to v plus delta v. We do not know if delta v is positive or negative as of now. Okay, so we will just keep it like this. And the radius has changed from r to r minus delta r. Okay. So if we compute momentum, it is mv. If you compute momentum at t plus delta t, it is m minus delta m v plus delta v. Okay. So if we compute delta p delta t, limit delta t goes to 0, which will be, so this mv will cancel out. So essentially we will have m delta v by delta t minus v delta m by delta t. So which in differential notation is simply m dv dt minus v dm dt, which is equal to F external according to Newton's second law. But because in our case it has been mentioned that there is no external force on this particle, what we can do is we can simply put a 0 here. So essentially the equation we will be working on is this. Okay. Great. Now what we can do is, so you see, as I said already during this during the discussion of system with variable mass, there is no unique way of writing this differential equation. For each of these problems, depending on the nature of the problem, we have to modify the differential equation. Only thing is we have to calculate the momentum change over a time delta t by taking momentum at pt and pt plus delta t and compute the difference. So we see that because the mass is evaporating from this raindrop, it is or water droplet, we are getting a different equation. Generally we have a plus sign here. When the raindrop is falling through cloud and it's accumulating moisture, we have a plus sign. Here we have a minus sign. Anyway, so let's try to integrate this, and what we see straightforward is dv by v is equal to dm by m integration. Let us assume that initially at time t equal to 0, we have a velocity v0 and the upper limit of the velocity is v. Okay, I'll just write it slightly below so that you can see properly. So v0 to v dv by v equal to integration. So, initially let us say the mass was m0 and at time t the mass is m. So, we have dm by m. So, integration will essentially give us a relation which is v equal to v0. Please remember that v0 is also a vector quantity. So, we are this left hand side of the integration is a vector, we are integrating vectors. So, keeping the direction intact because we do not know which way it will going to change. So, we have m0 m by m0. Okay. So, if we take this equation, we will have a logarithm, and then we have on left hand side we have v by v0, and right hand side we have m by m0. Comparing, we get v is equal to v0 times m by m0. Okay. So, v0 is the initial velocity, m0 is the initial mass of the droplet at time t equal to 0. Okay, very good. Now, question is how to get a functional form. So, essentially what we would like to do is we have to have m as m of t. Only then we can express v as a function of temperature, function of time, not temperature, sorry. So, in order to do that, please recall that we have another relation given, which is the rate of evaporation is proportional to instantaneous surface area for this droplet. Now, if that is the case, that essentially means rate of evaporation is dm dt, which is proportional to instantaneous surface area, which is 4 pi r square for this droplet, r being the instantaneous radius. So, r essentially is r of t, okay, and we have a proportionality constant k. So, k is, please do not confuse it with the constant for let us say resistive forces and all, it is just a proportionality constant here. Now, we also can write m is equal to 4/3 pi r cubed rho, rho being the density of water. Okay, fine. Now, if we do that, we can also get an expression for dm dt as 4 pi r square rho dr dt. Now, if we compare this expression with this one, we immediately see that comparing this to 4 pi r square cancels out. So, this whole term cancels out, leaving behind dr dt is equal to k by rho. Oh, sorry, there will be a minus sign here because as the water evaporates from the surface, dm dt has to be negative quantity. So, we have to put a minus sign here. So, we have dr dt is equal to minus k by rho. Now, we integrate that, we take dt to the other side and integrate. At time t equal to 0, we have a radius r0. At time t, we have a radius r. So, this integration gives us a relation which is essentially r equal to r0 times r minus, so r minus r0 minus k by rho t. So, this is a relation which we have in hand. Now, this is one relation and we already have another relation that v is equal to v0 times m by m0. So, what we can immediately do is, so at t equal to 0, r was equal to r0. So, put t equal to 0 here, you will get back r0. So, what we can do is, we can write m by m0 as 4/3 pi r cubed rho divided by 4/3 pi r0 cubed rho, which will be simply r by r0 whole cubed. Okay. And from this relation, we straight away know that r by r0 whole cubed is nothing but 1 minus k by sigma r0 t whole cubed. So, we use this relation to get our final expression, which is V is equal to V0 times k 1 minus k by rho r0 t whole cubed. So, this is the final answer. Now, if we examine this expression, we put t equal to 0, we immediately get V equal to V0. We put t equal to, let us say, we just write this as V0 times 1 minus t by t0 whole cubed, where t0 is rho r0 by k. Okay. So, if we have t is equal to t0, then we immediately see that V becomes 0. So, essentially it starts with an initial velocity, the droplet starts with an initial velocity V0, and at time t equal to t0, when time reaches t0, the velocity becomes 0. Velocity of the droplet becomes 0, and also at time t equal to t0, we can actually find the radius when it comes to a standstill. Okay. Anyway, that is not terribly important, just to give you some insight of this result. You can do it yourself if you wish. Okay. So, with this we move to the next problem, which is this one. So, it is a problem where it says that there is a balloon with a constant mass m, and it has a bag full of sand m0 in it. Okay. So, there is a constant upward thrust on the balloon, which is given by c, and initially it is in equilibrium. Now, once the sand starts releasing at a constant rate v equal to constant rate alpha, then there is a change in velocity. So, the balloon essentially moves upwards. So, we do not have to solve for the equation, but we have to set up the equation of motion for this particular system. Now, in order to do that, let us get into this picture once again. So, we have a balloon which has a fixed mass m, capital M, and there is a sand bag which is at time t equal to 0. This is the situation. Now, as the time progresses at any arbitrary time t, this sand bag starts releasing sand at a constant rate alpha. So, this mass is not m0 anymore, but this mass becomes m0 minus alpha t. Okay. Fine. So, now if so essentially what we have to do is we have to write the equation of motion for this particular system at any time t. Now, in order to do that, so please recall that the balloon in this situation, the equation of motion generally is given by m dv dt equal to f external. Now, this f external in case of balloon, so there is a upward thrust which is given by c in this case, and there is a downward pull which is given by mg. Okay. So, your net external force is c minus mg, because as the sand is getting released, the balloon mg component is decreasing. So, the balloon is moving upwards. So, the net external force is pointing upwards, so as the velocity. Okay. Now, because they are both in the same direction, immediately we can get rid of this minus so vector sign, and we can write this as dv dt equal to c by m minus g. Okay. Right. So, this is what we have in mind. All we need to do is we need to replace, so to set up the equation of motion, we need to replace c and m with some other quantity. So, essentially or c is also okay, because c is already given, we can essentially have to replace m. Now, in order to do that, we can replace m by m0 t, which is a valid substitution, m0 minus alpha t minus g. We can, so this is one form of equation which is already good. Now, please remember, we can have a slightly different version of the same equation, because there is another condition given that initially the balloon is in equilibrium. So, at time t equal to 0, when the mass of this whole thing is m0, not m0 minus alpha t, it is in equilibrium. So, that means C is equal to m plus m0 times g. So, we can replace this for C. Similarly, at time t equal to t0, the entire sandbag becomes empty. So, we immediately see that if we put t equal to t0 here, this whole term should vanish. So, we have m minus alpha t0 equal to 0, which gives us alpha is equal to m by t0. So, if we want to, for certain purpose, we might need to modify this equation, modify this particular form of equation. So, we can use this two relation to get rid of C and alpha if we wish. Okay. Anyway, so this is some manipulation, some modification of this particular equation can be done, but as of now, this is a very valid equation. If we want, we can put any of this this expressions into it, and we can modify this equation. So, I leave it on you to, as an exercise, to modify and play with the equation, and of course, you can put some values for different parameters and see what is the final equation look like. And this expression, as we can see, as it is, it's a very nice integrable term. The first term will give you a logarithm, second term will be just be proportional to gt on integration. Okay. So, let's move to the last problem of this particular section, and the problem is this one, number 4. Okay. Sand from a stationary hopper falls into a moving conveyor belt at the rate of 5 kgs per second. Conveyor belt is supported by frictionless rollers. It moves at a constant speed of 0.75 meters per second under the action of constant horizontal external force F external supplied by a motor. So, we have to find the sand's rate of change of momentum in the horizontal direction, which is along the x direction, and also we have to find in B the force of friction extended by the belt on the sand. Okay. Now, in order to do that, please recall that in this particular case, equation of motion is given by V dm dt is equal to F external. This was discussed in one of the previous classes. So, rate A, we have to calculate the rate of change of momentum delta P by delta T. Okay. Just a minute here. Rate of change of momentum, and rate of change of momentum is simply given by delta P by delta T, which is in this particular case is V times dm dt, and it is given that V is equal to 0.75 meters per second and dm dt is equal to 5 kg per second. So, we just put these numbers and we have 5 into 0.75 kg meter per second square, which is nothing but Newton. So, essentially we have 3.75 Newton. Okay. It should also be equal to the external force, because as the conveyor belt is moving at a constant rate, constant velocity. Okay. So, this has to be equal to the external force. Now, in part B, we have to calculate the force of friction. Now, please understand this, as the sand from this hopper hits the conveyor belt, the sand does not move anymore. Okay. So, if the frictional force, this can happen if the sand is not moving, this can happen if and only if the frictional force which is exerted by the conveyor belt on sand is exactly balanced by the force that is acting in the horizontal x direction. Okay. So, that means frictional force F friction will exactly be equal to dp dt in this case, which will be exactly equal to F external, and all these numbers are the same, 3.75 Newton. So, that is a pretty straightforward problem, and I hope you understood all the 3-4 problems we have discussed in this section. Now, let us move to the next section, which is the rocket motion. Okay. So, what we have here, what is special about rocket motion is so far we have discussed systems where the mass loss or mass gain is typically at 0 relative velocity. So, for example, when a raindrop is falling to cloud, it is gathering mass at and the gathered mass has no velocity on it. If the sand is leaving the balloon, the sand and the balloon at the point when the sand leaves at the time point, that particular sand particle and the balloon has the same velocity. So, the relative velocity between the mass and the big mass and the mass which is lost has been same. But rocket is different in that sense, because what happens in a rocket is we have a full fuel tank which is filled with fuel, and there is a combustion engine which burns this fuel to create hot and hot gas, and it exhausts the rocket in form of a jet, okay, which has a very high relative velocity with respect to this rocket body. So, the situation here is slightly different. Now, if we try to construct an equation of motion, once again there is no standard rule for it. We have to take this as a separate case, and we try to calculate the momentum. We try to once again construct the momentum at time t and a later time t plus delta t. So, let us see. Okay. So, at time t we have a mass of rocket which is mt, and the rocket moves in this direction with a velocity vt. Rocket at time t plus delta t, let us assume that it has lost a mass, or I will just use, there is a reason why I will use capital M for this, okay, because minus delta m, okay, and the velocity has gone from v to v plus delta v. Now, what happens to this delta m amount of mass? The delta m amount of mass is exhausted. So, this is your delta m amount of mass that has been exhausted in form of gas, jet of gas, and this leaves the rocket with a relative velocity u, or with a velocity u, which is measured with respect to the frame of the rocket. Please understand that frame of the rocket is an accelerating frame. A rocket in general accelerates. Okay. So, when it accelerates, it is not a relativistic, I mean it is not a inertial frame anymore. So, this velocity u, which is measured, which is given here, is measured with respect to rocket frame. Okay. Now, if we, and the velocity v here, which we are calculating, I mean which we are writing here, this is measured from a inertial frame. Because please understand this, the conservation of linear momentum and conservation of angular momentum, we will see the angular momentum part later on, these are valid in an inertial frame. These two conservation laws are not valid in a non-inertial frame. So, essentially when we are writing the expression for p of t and p of t plus delta t, we have to make sure that we are writing this expression with the velocities measured from an inertial frame. So, in this case p of t is simply m times v, okay, and p at t plus delta t is m minus delta m times v plus delta v, but there should be an additional term here, because this one, it is moving in the opposite direction of v, with a velocity u, which is measured with respect to rocket. And please remember that rocket is moving with a velocity v in this direction. Okay. So, the relative velocity at which the gas leaves the rocket body is given from an inertial frame as u minus delta v. You can also write u minus delta v minus u minus v minus delta v, but we will see that that will not affect the calculation that much, for a simple reason that this we will see in a moment. Okay. We can also write this. So, and this is going in the opposite direction, because this mass essentially is there is an jet of exhaust gas which leaves the rocket body. Okay. Now, if this is happening, then this momentum has to be subtracted from the initial moment or this total momentum, and then we will have delta m times u minus v minus delta v. Okay. So, we compute delta p, which is p t plus delta t minus p of t. If we go term by term, we have m v minus delta m v plus m delta v minus delta m delta v minus delta m u plus delta m v plus delta m delta v, and then we have to subtract minus mv from it. Okay. So, we see that immediately this mv cancels out. Okay. So, this delta m delta v cancels out nicely, and also so this term delta m v cancels out, leaving behind. So, delta p, or rather I will simply write dp dt equal to m dv dt minus u dm dt, which is equal to f external. Okay. So, this is our equation we have got, but still there is a slight manipulation which we need to implement here. This dm dt is the rate at which exhaust gas has been going out of the rocket, but we want to write the final equation in terms of the rocket mass m. So, if we substitute dm dt is equal to minus dm dt, the final rocket equation becomes m dv dt equal to minus u dm dt, or rather m plus u dm dt equal to f external. Okay. And here the m is the final is the rocket mass. Okay.